Hello, my name is DavidBerghmans, and I would like to present you our new instrument, the Extreme Ultraviolet Imager on board the Solar Orbiter mission. Solar Orbiter was launched on February 10, and on the right you see Solar Orbiter when it was still in the clean room. We have a heat shield like Parker Solar Probe, but what sets us apart from Parker Solar Probe are the little doors through which the remote sensing instrument can take images from the solar disk. There are 5 remote sensing instruments visible here. There is a 6th one on the other side of the spacecraft, and I will be telling you about EUI, the Extreme Ultraviolet Imager. EUI is the size of a big shoebox, and inside that shoebox we have 3 telescopes. One full sun imager that takes images in 2 wavelengths, 17.4 and 30.4 nanometers. And then we have 2 high resolution imagers, respectively in Lyman alpha and in 17.4 nanometers. It took us 3 months after launch to get to the first light images, which you see on the right, the very first ones. On the top, you see the 2 FSI images in 3.04 and 17.4. And at the bottom, you see an image in each of the HRI telescopes. Ignore the red technical jargon printed on top of it. What I want to discuss here a bit is the field of view and the plate scale of these telescopes. The HRIs are subfields, so they won't see the full sun. They see a field of view of 17 arc minutes. And they have a plate scale of half an arc second, which is comparable to SDO. The plate scale of FSI, in contrast, is slightly bigger, so worse than good old EIT. But FSI has an enormous field of view of almost 4 degrees. Now, this field of view and plate scale of this telescope is a bit weird at 1 AU. But they are designed to be sensible at 0.28 AU, the extreme perihelion that Solar Orbiter will reach. At that distance, the plate scale of HRI, of the 2 HRI telescopes will be 100 kilometers. For HRI UV, the spatial resolution will be actually 2 pixels, so 200 kilometers. For HRI Lyman alpha, it's a bit bigger or worse the spatial resolution, because there also the wavelength and the aperture limitation comes into play. FSI will have only half the spatial resolution of SDO at perihelion, but it will have a very big field of view of 4 solar radii, which will show us the outer corona all the way up till the Metis coronagraph. But it will also show you the full disk, even if Solar Orbiter is off-pointed to the limb. Okay, these are not our first light images, but our first weekly sequence of FSI, which was taken mid-June while we were almost at half an AU. This here is a demonstration of what we call connection signs on Solar Orbiter. It's an attempt to link what the in situ instruments measure with what we see in the remote sensing images. This was work done by the team of Tim Horbury in collaboration with Luciano Rodriguez and Bogdan Nicola from my team, where the location of the in situ source point is plotted here in green. I hope you can see it. I'll point to it with my cursor. And as if the movie plays, the green cross jumps up and down and tries to follow apparently follows the edge of the coronal hole. It's interesting to see that it follows these dark extensions of the polar hole, these dark fingers, let's say, and that when it is done with one finger, it suddenly jumps to the next finger as apparently the magnetic connection is changing. This is an early attempt to do this connection sign, so it was done by ballistically propagating the solar winds backwards to the PFSS solar surface, and from there on follow a magnetic field line down to the surface. And so that brings you to the edge of the coronal hole in this movie. It's an early attempt, as I said. More results or more sophisticated attempts will follow. But based on commissioning data, this was already very promising what Solar Orbiter can possibly bring. Similarly, in the category high resolution science, we had an interesting sequence from May 30, the end of the commissioning phase, when Solar Orbiter, here on the right, EYFSI, was 30 degrees off with respect to the Earth-Sun line. So that's SDO AIA, where you see that the zero line here and the meridian are in the exact middle of the SDO image, while here they're the 30 degrees off. The white square is the HRI field of view mapped on both images. And we have a sequence in that field of view of in both the Lyman Alpha telescope and the HRI UV telescope. I show you here a little zoom in of part of that HRI UV sequence. It's totally unprocessed data, so it looks a bit raw, but that's partly on purpose. We were at half an AU when this movie was taken, and so our 2-pixel resolution here is 360 kilometers. These smallest features that you see in the white rectangles are loop-like brightenings, the smallest of which are only those 2 pixels big, so that's why we are confident that our telescope is pixel limited, the resolution of it. And these little brightenings have been called campfires in an ESA press release in June. Now, these campfires are presumably sort of small nanoflares or an extension of what we called nanoflares before. I show you here a rather big one in HRI EUV and HRI Lyman Alpha, and the same thing again here, a bit zoomed in. The red square and the red dots is the identification of the event with the automated software that we made. And below here, you see the same feature in different SDO wavelengths. In this case, it's easy to recognize the same feature in SDO. Now, in the other case here, the feature is clear in HRI UV, but you don't see it in SDO, or it's only marginally visible if you're very carefully looking. Now, this feature is clearly smaller, and so it looks like we have discovered or identified new features, smaller features than were visible in previous instruments. Interestingly enough, none of the campfires that we see in HRI UV is seen in HRI Lyman Alpha. So it looks like these are purely coronal events, although each of these campfires, they happen at the chromospheric network. It's never in the cell interior, it's always on the network pattern. Since we have data from both EY and SDO, we can run triangulation software. This is the software by Bill Thompson in the SolarSoft. It's called SSE Measure, and you click on one image, the HRI image, where you see the feature, and it will plot you an epipolar line through the SDO image where the feature should be. If there is an identifiable feature in the same epipolar line, you can click again on it, and the software will tell you the 3D position of the feature, and from that you can deduce the height above the photosphere. Now it's interesting to compare that height with the length as we see it in the feature. This is in this case it's a somewhat circular event, but as I told you, most events are loop-like, and so you can measure the length. And from a semicircular loop, you would expect that the height is the radius of the semicircle, and so twice that height should be the length. If your brightening has this configuration, it would be on this black line. If it's somewhat flatter, it would be below the line, and if it's somewhat elongated upwards, it would be above the line. Now, by the work of Magdalena and Andre and Luciano and Samuel, it turns out that for a subset of these campfires, they're all significantly above the 2H equals L line, which means that they would appear at first sight as elongated. So they're given their lengths, it appears that they're higher than what you would expect from a semicircular loop. Now, this is just a cartoon. We are not claiming that all loops are like that, quite the contrary. What is more likely is that the length of the loop, so the distance between the foot points, is somewhat underestimated. Possibly we're only seeing in the UV the apex of the loop. So the top would be brighter in the UV than the rest of the loop. And so we're underestimating the length of the loop. And this can possibly happen, for example, when two loops have a reconnection event where they touch, such that only the loop tops brighten up. There is one image that HRI UV took, exactly one that HRI UV took of the solar limb. And in that image, which has been sharpened a bit, that's why it looks a bit noisy, you don't see any single one tall loop. All of them look rather a bit flattened out. There are also Eiffel Tower jet-like structures. But so most loops look like flattened, and the most likely explanation therefore is that we only see a part of the loop length, and that another part is hidden deeper in the chromosphere and not emitting in the UV. More campfire results will be presented later in this session by Louise Harra in her talk on campfires. Now, up till now, all what I presented to you was commissioning and cruise phase data. We will continue being in cruise for another almost a year. And this is, here I plot you what we see in the first half, or the situation we will have in the first half of 2022. The Earth and the Sun in this graph are static, and the solar orbiter orbit is the black line that turns colorful here for the first half of 2022. So when we're at the blue triangle, that will be on March 8th, we will be exactly on the Sun-Earth line, but after that we will gradually go to perihelion, but also more to the west than the Sun-Earth line. So that's what I'm trying to plot here. The square is the HRI UV field of you, which gets smaller and smaller as compared to the disk as we approach perihelion, while the Sun-Earth line, the yellow square here, gets more and more towards the limb as seen from solar orbiter. So all that happens in just 2 weeks. So for sure, these 2 weeks we should coordinate with earthbound instruments, and I'm sure that will be very interesting data. So for now, I have to conclude that EY is successfully commissioned on board Solar Orbiter and on track for interesting science. We still have to do some technical optimizations, which will take us most of the 2021. Despite that, we have already first science coming in the category connection science, but also high resolution, the campfires. And it looks already now very clear that whenever we do EUI data analysis, we will want to compare it with earthbound instruments, and we will have to do some stereoscopy to compare these, since the solar orbiter perspective is changing all the time. I only want to finish now saying that EUI is brought to you by a very large team from 7 different institutes. And if you want to learn more, please have a look at the instrument paper, Rochus et al. 2020. You can also get the data yourself on these websites. And if you still have questions after this session, you can email us and we'll get back to you.